please give me a sign. And I will start just introducing ourselves. So I will be the first speaker. I'm Laia Perez-Simbor, and I'm project manager at the European Copper Institute. And our second speaker will be Andrea Bakary. She is the director of the Health, Environment and Sustainable Development at the International Copper Association. And just to start, I would like to explain the objectives of today's session. First, we will introduce a bit what are those indicators in product design that assess resource efficiency. Then we will explain inside those indicators whether abiotic depletion potential could be one of those. And finally, we will propose 3 indicators to assess resource efficiency in product policy. So, first part, I will be the speaker and we'll go through which are those product design indicators to assess resource efficiency. And I think it's worthy to start to speak about the need to include resource efficiency with the classical circular economy wheel. So it is clear that populations are growing and economies are growing as well, and the use of resources is indeed a challenge for most of our countries. And there is a common trend to actually keep those resources in use to the most of possible. So indeed, going towards a resource efficiency economy is an effort at many levels that could include design, recycling, disposal. One may think that the most important step to actually boost a circular economy is recycling. Others could think that perhaps boosting reuse of products, perhaps creating a second-hand market, but indeed, there is a growing trend at the European Commission and also in Europe to include resource efficiency aspects in product design. It's a trend that is growing, and indeed, and we will discuss later on what those trends are. So, first question will be, how can we search for those indicators in product policy that help us to design sustainable resources? And for that, I would like to present this wheel. It's kindly inspired by OECD's wheel on sustainable consumption and production steps. And as you see, those steps in this wheel represent how policy should tackle the resource efficiency aspects on product policy. So of course, the first is sustainable resource management. The second step will be design for sustainability. Of course, we want to produce products in a cleaner way, and we can use sustainable transport for that. And then we have the step of eco-innovation. And here we have the clear example of eco-design, which one of the final goals is indeed creating a label of energy performance. So that could be some kind of example of certification. And this is the case as well for green buildings and BREEAM, LEED, and other certifications. Another important step is sustainable procurement. An example of this will be, for instance, guidelines to local authorities to purchase goods that are considered green, that are certified as green products. We have sustainable market and sustainable use. And here the clear example is eco systems in washing machines, dishwashers, and of course a sound waste management. But indeed, even if we have examples of policy at many levels of sustainable consumption and production wheel, design for sustainability and choosing the right indicators for design for sustainability is still an area of development. I would like to introduce 3 European initiatives that are actually looking for those indicators in product policy. And I would like to start from resource efficiency indicators in buildings. This project aims to define a common framework of indicators for assessing the environmental performance of buildings. It's a project that is due to finish in 2017. Currently now, we have already the first task of this project, which is defining those macro objectives. So instead of starting for the indicators and the clear formulas for those resource efficiency indicators, the project has first defined which are the priorities for buildings. And here, the message is clear. For material efficiency, the best is optimize building design, engineering forms, extend the long-term material utility, and of course, at the end, reduce significantly the impacts. And if we come back to the wheel we have presented initially, in terms of building, instead of products for buildings, two main steps: design for sustainability and sustainable use. The second initiative is the one related to electric and electronic devices. So this includes, for instance, washing machine or vacuum cleaners, as many others, and are those devices that are included in the scope of the Eco-Design Directive. In 2013, the Eco-Design Directive firstly tackles the energy use of those products, but in 2013, a report already mentioned few indicators that could be included in the eco-design in order to not only boost the energy efficiency of products, but also the material that those products use how to target this efficiency of this materiality and how to create those indicators for that. So the report concluded 4 clear indicators. One is recyclability benefit rate, so quantify or targeting this amount of material that can be recycled in the future. The second indicator is recycling content, so quantifying this amount of material in the product that indeed has been already recycled. The third indicator is regarding lifetime, and finally critical raw material indexes. So if we come back to the wheel of sustainable consumption and production, those 4 indicators clearly target the design for sustainability step. In this project is the first time that we heard about abiotic depletion potential, and although was considered in the assessment, finally was not selected due to the inconsistencies in the characterization factors. But indeed, the challenge is taken by the European regulators to include resource efficiency seriously, and in 2015, the European Commission issued a mandate for standardization of methods on resource efficiency to CENELEC, which are the European bodies of standardization. The objective is clearly to have methods, tangible formulas, measurable results that could be applied ideally to all products inside the scope of eco-design. And among the objectives of this mandate is clearly targets methods to quantify and extend the lifetime of products, quantify and the amount of reused components and recycled materials inside products, and the recyclability of those materials in the future. Abiotic depletion potential is not considered, and again, if we come back to the wheel, we see 2 clear steps. They target design for sustainability, but also sustainable use. And I would like to introduce the third initiative that actually tries to quantify resource efficiency in products, and is the product environmental footprint. This initiative is based on life cycle assessment and tries to create a system that is able to benchmark products, to compare products that at the end eventually be included in eco-labeling schemes. This method of using exclusively life cycle assessment indicators to assess the environmental performance of products has been highly questioned. And indeed, this study is in a testing period. There are three main indicators that we could, inside life cycle assessment, propose by this initiative that target the use of resources. And this resource depletion water, resource depletion mineral fossil fuels, and land transformation. Considering that resource depletion mineral fossil fuel is the same as abiotic depletion potential, so it's called in a different way. And there's two surprising things of this methodology proposed. First, that the indicators in this case does not necessarily target the design of the product, but they go a step before, assessing the sustainable use of resources. And in this case, and in contrary to other reports, the abiotic depletion potential is considered as a robust indicator. So let's recap a bit what are the considerations of product policy and the trends to include resource efficiency. So the majority of studies propose to assess resources in sustainable consumption, but at the design phase. And there is a clear trend to include in these concepts the extending the life of the product, quantifying the recyclability and the recycling content of those products. The indicator of life cycle assessment, abiotic depletion potential, has been considered not robust enough for eco-design. However, it's included in the Commission's product environmental footprint, and studies have shown that there is a tendency to skew the results. But what do we mean by that? So I would like to explain two examples. These are examples taken from the pilot test of the product environmental footprint of two products. The first one is an uninterruptible power supply, so UPS. This is a product that, because they are an energy-related product, could be actually used in the co-design directive. And here we see what is the environmental performance of the first draft. As shown in the arrow, the ADP indicator is large. It actually drives a bit the conclusions. And the discussion of the report of UPS is indeed a cutoff was needed in order to guarantee a feasible and extract conclusions from the report. So the question is that really an indicator that is helping us to improve resource efficiency in products? The second example is IT equipment. Again, a product that could be used or could be inside the scope of the eco-design directive. And here in this case, the same appears. The environmental performance seems to be only defined by the ADP. And one wonders if it's really meaningful, if it's a meaningful assessment, what it means, and if it's really helping us to improve our resource efficiency, the use of this indicator. So the question that we want to ask is abiotic depletion potential an unsuitable indicator? And why is an unsuitable indicator? And for that, please let me introduce Andreas Bakari's expertise. And thank you, Andrea. I give you the floor.
Thank you, Laia. So in this section, we're going to explore in detail how abiotic depletion potential works, what the developments have been over the years with regard to it, because it was actually first developed back in 1994, and where it stands today in terms of its utility and some of its main weaknesses that we see. In the ISO standards for life cycle assessment, there are some criteria that are laid out for impact assessment. Abiotic depletion potential is an impact assessment category, or what we call an impact category that's utilized in life cycle impact assessment. And what ISO says essentially is 3 to 4 really key points. One is that the characterization model that sits behind the method, so how abiotic depletion potential is calculated, should be internationally accepted. So for example, based on an international agreement or approved by a competent international body. Examples of that would be ozone depletion potential that's utilized in LCIA, which was all of the characterization factors are based on an agreement made called the Montreal Protocol many, many years ago. Or global warming potential, behind which the characterization model sits that is put forth by the Intergovernmental Panel on Climate Change. There are other requirements here that I won't go through in detail, but if you look to the bottom of the screen, you'll see essentially that the characterization model for each indicator should be scientifically and technically valid and based on some sort of distinct identifiable environmental mechanism. And that environmental mechanism we'll come back and talk about in just a few minutes. Also, the extent to which the characterization factors, which are generated from the model, are scientifically and technically valid needs to be identified. And then the category indicators should be environmentally relevant. And the reason for that is that the ISO standard for life cycle assessment is based on environment. Currently, globally, in life cycle impact assessment, in the broader life cycle community, the most commonly utilized and agreed upon categories include global warming potential, ozone depletion potential, both of which I mentioned previously, photochemical oxidant creation potential, which has different names but essentially looks at smog, acidification potential, and eutrophication potential. And this is due to the availability of models that have one or more of the following, which were essentially presented on the previous slide: international acceptance via global agreements, clarity of the impact area, robust regional models, and depth of research to date. Impact categories that have the greatest variability or uncertainty, and in some cases least agreement globally, include resource depletion, of which abiotic depletion potential is a method, human toxicity, ecotoxicity, land use, and social impacts. And that's because these categories require some accounting for space, time, uptake, basically what we would sum up as complexities that LCA is not particularly suited to. As a result, there are many different opinions on methods and models, and you'll see a little bit later in my slides, in some cases for these different impact categories, you can have upwards of 15 to 20 different models being used to calculate characterization factors. The European Commission funded a study, a very thorough study that was done several years ago now. It was published back in, this particular article was published in 2013, but the report for the study came out in 2010, and it's referred to as ILCD, the International Reference Lifecycle Data System. The project was developed by a very broad group of experts and stakeholders in life cycle assessment, and is seen by many as a global reference guide for LCA practitioners. In the 2010 summary report on impact assessment methods, the team stated that the greatest needs for improvement in terms of impact assessment were around the models that are utilized for human toxicity, ecotoxicity, land use, and resource depletion. And in fact, specifically, they pointed out that for resource depletion categories, the impact category itself is not very well defined. The analysis is, their analysis, was hampered by insufficient understanding of the area of protection. We'll talk a little bit more about the area of protection concept in a few minutes, and hence really what was the issue to address by the characterization modeling of resource use. At the same time, they recommended a switch in denominator. So we'll talk in one moment about how ADP is actually calculated. But essentially what they recommended was a switch of denominator from ultimate reserve, or what we'll come to refer to as crustal content, to the reserve base, which was then adopted by PEF. But the original authors have come forward to say that this is inappropriate and should be switched back to ultimate reserve or crustal content. So let's explore what do we mean by that. ADP is a very simple calculation. Essentially, what you're looking at is taking the basically the output of or the input, I should say, of the life cycle assessment. So you take the life cycle inventory. Let's say we've utilized to make 1 kilogram of copper. We've utilized X amount of a particular kind of resource. So let's say oil or water, or let's say, for example, copper. And so essentially what it does is it takes that total amount for your functional unit and multiplies it by a characterization factor. And in this case, the characterization factor is determined by, in the original model, was determined by crustal content, which essentially is the total global stock or the total global amount of a mineral or metal in terms of geological availability. We'll look at that again in a few minutes. There's also an option to look at it via the reserve base or mineral reserves, and we'll explore each of those in detail in a moment. But essentially, as you can see, the calculation is essentially the abiotic depletion potential of the resource, the quantity of the resource that's been extracted, so the amount per functional unit, the assumed stock of the resource, the extraction rate of the resource, the assumed stock of the reference resource, which in this case is antimony, and there is no scientific reason for selecting antimony. Essentially, the idea was just to choose something for which they felt they had a lot of data with to compare, to provide a comparison and index the reserve. And so essentially, antimony ended up being selected, and the results are then actually reported in antimony kilogram equivalent. Because of the calculation and the way that it's done, as you can see, it's very much denominator driven. So in the denominator, we actually have that calculation of how much of a stock there is based on a different criteria. Because of that, it is obviously very dependent on what's in the denominator. So for example, if I look at copper, or I look at, let's say, boron, or another element or metal, the amount that's available in the crustal content is actually determined from previous studies that have been done in the industry to determine how much is available in the crust, so in the Earth's crust. And so Rudnick and Gao published a famous study back in the 1970s that took the original numbers, which were often referred to as Clark numbers, and went and did several samples at varying depths in the crust globally to look at ratifying the original numbers that were developed around the turn of the 20th century by Clark and Washington. And essentially what they found was that those numbers were still very, very close. But essentially what you get is a percentage in the crust, which then you can develop an estimate, of course, based on what we presume to be the weight of the crust. Next, reserve base has been used in the life cycle community, and essentially what reserve base is essentially the reserve base numbers that are published by the USGS, or used to be published by the USGS until about 7 years ago. And that's essentially the global reserves that are available. And then there's mineral reserves, which are essentially those that are deemed to be active in-play reserves in the world market currently. Initially, crustal content was used, as I described earlier, and was then further developed by Urs et al. In 2002. So Guinea initially developed the method in 1995 as part of his thesis, and then Guinea and Hyungs worked together to develop characterization factors based on crustal content on that Rudnick and Gao study. And then Urs et al., which is basically Van Urs et al., took that and took it to the next step. So more characterization factors as well as a few alternatives to the baseline method of using crustal content. Later, as I previously mentioned, the ILCD sponsored effort then recommended changing from crustal content to the reserve base. As you can see, I've quoted here, due to its longer time horizon and possibility of improvement in mining technology, making feasible the exploitation of previously sub-economic deposits. But what happens when you do that is you go from looking at a very big global stock to a much smaller number that is based on, in fact, constantly fluctuating factors in the economy. The original authors of this method of abiotic depletion potential, Guinea and Urs, just released a paper in the last 2 months, basically, to come forward and say that they feel this is inappropriate and it should be switched back to crustal content. Why is it inappropriate? If you take a look at this particular model, essentially what we're showing here is, if you imagine at the bottom of the diagram, the Earth's crust. So we have that number. We have a number. We know that if we go and take a section of the Earth's crust at any point around the world, we'll come up with a number within reason of, or a percentage of a given metal or mineral. It's comprehensive. It's a representative number that's been shown over time by geologists. And it's a stable number. It doesn't change. Rudnick and Gao showed that over 100 years of research, they weren't able to improve the numbers very much, certainly not in a statistically significant setting. Then we have this number that we would all love to know. So how much of that crustal content could be extracted, say, over the next 500 years? It's been studied time and again. It's been studied by Gradle, Skinner, many of the key experts in stocks and flows, and just can't be robustly produced based on too many very, very broadly ranging variables. And then we have reserves and resources, or essentially what we refer to in the mining industry, obviously, as reserves and resources. And as we know, those are driven by many, 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 many economic factors. They can be driven by demand, politics and governance, discovery technology, extraction technology, access to energy, cost of capital, exchange rates. They really vary significantly over time, and they should. They are directly tied to economic variables. Here we have, on the right-hand side of the slide, you see 3 charts. Those 3 charts basically describe and show the mineral resources, mineral reserves, and then the global resources for 3 different metals. We have iron, copper, and indium. What you can see with iron is essentially that the iron ore reserve base has fluctuated with the economy over recent years, but the USGS estimate of total world resources has remained unchanged. It's been a very, very stable number over time. With copper, there has been so much development in the last 40 years. So essentially, the copper reserve base has continually increased over the same period as a result of frequent reviews of the estimate. And that reflects the general tendency for higher demand to stimulate higher exploration expenditure. In the early 1970s, copper resources, world resources, were estimated at 1.6 billion tons by the USGS. This estimate was then updated to 3.7 billion tons in 2006, and it's now estimated at 5.6 billion tons. And these are significant changes, 3.5 times what we once believed to be available or exploitable for copper. And then we see indium, which paints a totally different picture. Indium is a byproduct of zinc production. It's one that typically is very, very difficult to get good data on because it is a byproduct. And as a result, what ended up happening was the USGS in 2007 said, we can no longer produce reproducible data for the reserve base for indium, so they stopped. And that's a real challenge for methods like this that are essentially taking reserve-based data and using it to judge how to make a better or a more environmentally friendly product. If you have such poor data underlying the models, then you could be making the wrong decisions. So let's look at that a little bit more. How does that happen? So essentially what happens is, we take a look at this hypothetical example where we have product A and product B, and you'll see copper, indium, platinum, nickel, and iron are the key constituents in this bill of materials. If we then calculate the abiotic depletion potential using different denominators that have been used over time, we see vast variation in the results that we get. So CC in the x-axis, essentially here we have each of the methods for each product, for each of the denominators, I should say. And on the y-axis, you have ADP, which is reported in kilograms antimony equivalents. On the far left here for product A, you see crustal content and crustal content with extraction, which is just two different ways to do the calculation utilizing that data. Then we see the reserve base. So the reserve base in 1992, the reserve base in 1999, and the reserve base in 2009. And then further, you see the reserve data. So the economic reserves in LCIA terms and the mineral reserves in the mining industry language. And we see there's the same trend. So essentially what you see happening is that over time, the number decreased because the reserve-based estimates increased. And they increased dramatically across several of the ingredients or the materials that are utilized in this product. You see a similar picture over here for product B, but what's most interesting, and it's hard to see on this axis here, but crustal content clearly favors product A over product B, but the reserve base favors product B. And I apologize, I could make this larger so you could see it, but if you go to the paper that's listed at the bottom, you can actually see several more charts that go into more detail analyzing this. But essentially what we see, all this red you're seeing, is indium. And essentially, indium is driving the decision in this case. And what did we learn about the indium data a few slides back? That the indium data is in fact probably the worst data that's being utilized currently in this calculation. And the USGS, if you go and speak with their experts, they will tell you that. And so coming back to Laya's example that she showed us, you know, we see this IT equipment storage screening report result, and the numbers after they've been normalized show that essentially raw material acquisition or the mining part or recycling part of this product is what's driving all of the results. And in fact, because it is electronic equipment that utilizes indium and tantalum, that output is actually being driven by poor data, which I have to believe that most people would not want to see happen. You wouldn't want to drive a product design decision, certainly around poor data. So just quickly, how did we get so lost? How did we go from this idea in 1994, 1995 that we could estimate the reduction in a global stock that is consistent and stable to one that is not consistent and stable? Essentially, this area of protection concept, which we use in LCA, we basically say that meaningful impact assessment requires unambiguous area of protection, so a valid mechanism to link what you're studying in the product system to impacts on the area of protection. And so the area of protection, you know, for global warming, right, you know, is essentially the climate and the shifting climate. The area of protection for ozone depletion potential, you know, is that ozone layer. Having the ozone layer there, obviously, is better than not having it there. Having protection is better than not. And so in this case, what is the area of protection? It's a very difficult one to determine. Are you saying that we should leave all of the resources in the ground and never take them out, never extract them? And when we do, that's a bad thing? For metals, that's a very complicated analysis and a very difficult one because it doesn't consider the fact that once you extract it, it can be reused and recycled over and over and over again. And so it introduces this complication of, are we actually measuring something that's important to the environment, or are we actually, in fact, more interested in availability? So in each of these methods, and again, I won't go into detail with them, but the paper describes them further. What we see is this shift from protecting an original amount of a stock to actually being more concerned about how much is available at a given point in time of a mineral or a metal. And so essentially, 14,044 states that for a method to be viable and relevant, it must be connected somehow to the area of protection. But how do reserves provide any kind of an environmentally relevant indicator? If the AOP, or the area of protection, is truly the natural resource in and of itself, then the only relevant denominator is crustal content. Yet while crustal content is a stable number, to make it more relevant, we try to tie it to some indication of current depletion, which is that extraction rate you saw earlier in the calculation. But that's done using data that measures availability, not how much is in the fixed stock. And so we end up with this crossing of data at data points that don't make sense. And so we lose the connection to the environmental mechanism. And we don't take into account stocks and flows in the economy currently. And therefore, the indication of depletion is no longer valid for most metals. And really, are we not more concerned about availability? In the long term, you know, what we're more concerned about, certainly in terms of our political decisions and in our livelihood decisions, we're concerned about how long will something be available to us as humans to use as a resource. This is a quote, and I won't read it, but word for word, but this is a quote from the paper that Van Oort and Guinée just published in Resources, and essentially they sum it up very well. That really the problem refers to depletion of functions that natural resources have for the economy, and therefore resource depletion is basically an economic problem, not an environmental problem. They do take a pause and go on then to look at, okay, well, what if we shift it from just being a straight reduction in a global stock, or 1 over the stock times the amount of material used, what if we actually start to incorporate dissipation? So acknowledging that you have some amount left that can go on to be utilized again, but how much is just actually lost in terms of human use. So they presented some new information there. And essentially what it all comes back to is that different decision makers need different tools. And so we end up with this very unfocused attack at trying to, or attempt at trying to, develop impact assessment methods that suit everyone and all of those users. So in summary, ADP it's highly sensitive to the selected denominator. That's very clear to see. The math is very clear and easy to understand. Anything other than crustal content being utilized in the denominator introduces significant vulnerability and essentially shifts it to providing an indication of availability as opposed to depletion. And really, we have other methods for that. As Laia presented, we have other methods for that. We also have methods such as criticality for understanding that. And ADP should not be used alone as a standalone indicator in product design or assessment. It holds little relevance in the environmental context, as many, many authors have come forth and said. And other methods that incorporate durability, recyclability, recycled content should be developed. I will hand it back over to you, Laia.
Thanks, Andrea, and thanks for this clear explanation. And the question now is, well, we have understood why abiotic resource depletion potential does not develop robust results, but the question is, how can we include resources in product policy? Is there an indicator that could drive us to that? And for that, I would like to retake this concept. So different decision makers need different tools. And when we see this, we can think that governments may need an indicator that help us to understand which are those global stocks and flows, and where are those, and if they have good relations with that country. Financial investors of shareholders, they might be more worried about the price of those resources, about the price fluctuations. But when we talk about consumers, architects and designers, and those engineers, what they really need is an indicator that indeed helps them to do the most of the resources they have available. And To come back to the first question, searching for indicators on resource efficiency in product policy, it's clear that for those designing products, for designing to sustainability, indicators should target concrete measures that guarantee a real number that could be managed by experts in designing, but not necessarily experts in geology. And they give them solutions. Those indicators should give solutions for the short term. So what we propose is 3 key indicators. The first, durability. So we define durability as the ability of a product to perform its function in a given period of time or hours under conditions. So you have more information in the link attached on how this durability could be measured. But the advantages of having this clear definition of durability is that it helps us to assess one of the main concerns we have seen, life of products. It's focused on product design, and indeed there are several methods that of course could be used for different products. The second indicator that we will advise to assess resource efficiency in products is recyclability. So it's that amount of material that indeed could be recycled in the future because the conditions of this material, because the technicalities of this material, or because how this good is designed. And the advantages of this indicator is that it's focused on clear product design. And finally, we propose to assess resource efficiency indicators to quantify the recycling content of a material. So this amount of material that has been recycled already and is included in the product. So again, it helps us to assess how these components are recycled in products, and again, it's an indicator that could be focused in product design. So just to finish and clearly set some takeaways for you, it is clear that we have to include resource efficiency indicators in product policy, but this should be at the design level and known at the sustainable resource management level. We need concrete methods to calculate durability, recyclability, energy recovery, recycling content that help us to track the resources in products and that help us to do the most of those resources. As we have seen, the use of life cycle assessment indicators to assess resources, it doesn't give us a solution to increase the efficiency of producing of products, and the indicator abiotic depletion potential is unstable and is not suitable to assess resources at product level. So thanks to all, and please let me show you the slides with a reference that will be distributed in case you have further questions. And thank you, all of you.